what I want to talk about today is galaxies on the edge, and this is it's kind of a play on words at some level because what I'm going to talk about. Oh, my pointer's on. Okay, what I'm going to talk about is looking at no, I'm going to talk a lot about the James Webb Space Telescope. How many people have heard of the Webb? Yeah, okay. How many have you folks had any talks on the telescope before today? Maybe a little from the buildings, so there's other parts of not anything. Okay, so what I'm going to go through today is thinking about the telescope and why it's important and why it's so useful for astronomers. Also, thinking about the timescales about when it was launched, and in fact, how and when we got access to the telescope, and then how and when we waited for the data to come in. And then I'll talk and in a public setting for the first time show folks the data that we actually did get from the James Webb Space Telescope. Okay. All right. So this is the James Webb Space Telescope. Here it is, a CAD image of it from a computer that just sort of shows you what the whole thing looks like. And this is an image of the actual mirror in the Goddard Space Flight Center high bay. I like to tell people that this is the most Notre Dame of all telescopes because the mirrors are coated in gold. If you've ever seen the Golden Dome, it makes a lot of sense. But they're coated in gold because this telescope is designed to look for, to observe infrared light that has a longer wavelength than we can typically see with our eyes. And much of the light that it is able to study is at wavelengths that doesn't make it through the Earth's atmosphere, in part because of the life-sustaining molecules that are in the atmosphere, like water. Astronomers like to say that we could make amazing observations if we could just get rid of this pesky atmosphere of Earth. Okay? And in fact, actually, there was a Broke Reaper who was a very famous radio. He was actually an amateur. And in the early 20th century, he built the first, 1940. He built the first fully steerable radio in his backyard. And he was a little extravagant. Eventually, after he sort of got fed up with the US, he moved to New Zealand. And he was still pursuing radio astronomy, and he got really interested in very, very long wavelengths of light. So radio waves, whose the wavelengths are, I got started when I was an undergraduate doing radio astronomy, and studying wavelengths of light that were about, we studied the 21 centimeter line of hydrogen, which is, the size of the wavelength is the size of your forearm, essentially, right? Well, he wanted to study like meter scale wavelengths, and they don't make it through the Earth. So his idea was actually to send up a rocket that would explode and send some detritus into the upper atmosphere to disrupt the ionosphere so that he could through it shortly. All right. So astronomers have crazy ideas sometimes. Nonetheless, this is the James Webb Space Telescope in its high bay as they were getting ready to do the testing. Here it is, sort of what it would look like if it were fully deployed. It's a 6.5 meter mirror, as I'll say many times here, and it's shielded from the sun's heat by it's 5 layers of tennis court sized mylar type material. It's not exactly mylar, but the idea is there. Okay. And again, this gold color is because it's built to be sensitive to infrared radiation. Just to give a sense of scale here, this is a 2.5 meter or 2.4 meter diameter mirror that is the Hubble Space Telescope's primary mirror. This is what Webb's primary mirror looks like. Okay? Now, a couple things about this. Firstly, it's big, and that's important. That's important both for collecting more light, because the bigger you make your telescope, the more light it will collect. But also, when you put a telescope in space, how sharply it can see it can make images on the sky is related to, it's directly proportional to the size of the mirror. So a large mirror makes higher resolution images than a small mirror. Now, that's not the only effect, because it turns out that a large mirror for the same wavelength will make sharper images. Hubble tends to operate, for the most part, in the optical. So let's say 500 nanometers, which is right in the green where your eye is very sensitive. Webb works at wavelengths that are 10 times longer. And so actually the resolution, 2 to 10 times longer, 2 to 25 times longer, it turns out. Webb's size allows it to have about the same imaging resolution as Hubble's. They just operate in different ways.
And so this was the whole design goal of the Webb Space Telescope, was to access wavelengths where if you think about the electromagnetic spectrum, which is, the light that we see is right down here in this thin little slice. As you go to shorter wavelengths, which have more energy, you get to the ultraviolet. So the atmosphere of the Earth blocks this stuff out, thankfully, because otherwise we'd have real skin issues. Ultraviolet light, X-rays, and gamma radiation are detectable above the Earth's atmosphere. The Hubble Space Telescope isolates light from the ultraviolet through the optical and a little bit into the infrared. And the James Webb Space Telescope was designed to access this longer wavelength infrared radiation. Okay, so it was designed to see very, very sensitive or very, very faint infrared light. And again, this is just a comparison of the sizes where the Hubble Space Telescope has a diameter of, its primary mirror has a diameter of 2.4 meters, and the James Webb Space Telescope of 6.5 meters. That's 21 feet. I don't know, I'm never very good at doing this, but 21 feet is probably about here to the back wall or something like that, right? So it's a sizable mirror. Now you'll notice also that it's segmented. Okay, segmented meaning it's not just one, what we would refer to as one monolithic mirror, one singular piece of glass. It's actually, I don't even remember, what is it? It's about 13 or so, something like that. Hexagonal segments all kind of packed together. And when you look at it, unfolded, it looks like this. So this is, again, in the Goddard Space Flight Center high bay. You can see the primary mirror here. Are there people in this? Yeah, there are a couple engineers down here walking around. So you can see the size of this compared to people. There's a really, really small secondary mirror up here, supported by these three struts. Here again is the primary mirror. And what I want you to notice here is, wait a minute, that secondary mirror that would normally sit way up above the primary is now over there, because this whole structure is designed to be unfolded in space. And in fact, that's part of the reason that it's these hexagonal segments that make up the mirror. Because, well, two reasons. One is to make a monolithic mirror, they tend to get really, really heavy. And our typical launch costs, at least right now before the commercial stuff gets going really well, are about $10,000 per kilogram. Okay, so the heavier you make the mirror, the more expensive it is to get off the ground. The other thing is, at the time that we were designing the James Webb Space Telescope, no rocket existed that had a fairing that could hold a 6.5 meter diameter mirror if you made it into one monolithic mirror. So we didn't have a rocket that was big enough to hold a complete full 6.5 meter mirror. So the solution was this whole structure was made to fold up upon itself. So this is an origami telescope. Okay, here it is actually folded up. You can see the central region of the mirror is complete, but the wings on the outside, each of which contains, if I remember correctly, three of these hexagons here. There we go. Right. So these three and these three fold up behind the telescope. And when the telescope got on orbit, the first thing that it did was it unfolded these booms that hold the secondary mirror. They came down like this, and then it unfolded the wings back here. Actually, that's a lie. Okay, that's not the first thing it did. That's the first thing it did for the telescope. First, it had to unfold all of this heat shielding. Okay, and the reason for that is that in order to be sensitive to this infrared light, it turns out if you heat up something, like if you looked at one of these these might be LEDs, but if you look at an incandescent bulb and you work out where is all of its radiation coming out, it's coming out in the infrared more than even in the optical. And the reason for that is once you heat something up, it starts to glow. Like if you looked at us, we would glow at about the wavelengths that the Webb Space Telescope is trying to see. The problem with that is if you heat up your mirror, well, actually, let's think about it another way. When you go to set up your telescope, do you go and put that underneath a street light? And the answer is no. And the reason is that the glare from the street light is so bright that it makes it really, really hard to see the faint things that you're interested in. Well, with the Webb Space Telescope, if you let it heat up to 300 Kelvin, like the air in this room, it would glow at exactly the wavelengths that it's trying to look at. And so what that would mean is that in order to find the distant galaxies, you would be trying to see those against the glare of the telescope itself producing a bunch of light. So just like you don't want to set up underneath a street light here in Kalamazoo, you don't want the telescope itself to be the equivalent of a street light out in interplanetary space. Now, why is the infrared so important, and why did we design this telescope to study light in the infrared? You've probably all seen this image before or something like it, right? This is the so-called pillars of creation, made very famous by the Hubble Space Telescope imaging. If you look at this in the infrared, this is what it looks like. So notice these pillars become more ethereal. You can see through them. And in this image, if you look at it, in the infrared, there are hundreds of stars in the background. But when you go back to the optical, interstellar dust is absorbing the light from those background stars, and so you can no longer see it. So by going to the infrared, we can peer through the dust in galaxies, and we can see into these dense clouds where stars are forming for the first time, stars and planets. On a bigger scale, if you look at a whole galaxy, this is an image taken from the ground. To me, it looks like M81, but maybe you folks can correct me if I'm wrong on that. Actually, it looks like M81 taken from the ground, right? This is what it looks like in the optical wavelength. So wavelengths light you could see with your eyeball. The Spitzer Space Telescope, which is a predecessor to Webb, imaged this galaxy. And if you look at what Spitzer saw at wavelengths that Webb is sensitive to, this galaxy in the optical looked like that. Okay? So now notice how all of a sudden that sort of complex, all the dust that was there and the mishmash of stars that were very hard to sort of peer through because they were so bright, they start to look now like this. You can peer through those stars. You can start to look at the gas and dust that's forming stars directly. And so it gives you a unique view of what's happening in galaxies. In addition, like the Hubble Space Telescope in some ways was designed to try and solve the problem of the Hubble expansion of the universe, trying to measure how quickly the universe was expanding. That was one of its key projects. And in a very similar vein, one of Webb's key projects is to see the earliest galaxies in the universe. Now, why is the infrared important for that? You've probably heard from many other people that the universe we live in is expanding. And when a photon, a little packet of light, is trying to come toward us, so let's say it's coming toward us as a green photon. As the universe expands, and when we say expansion, it's not actually expanding into anything. What's happening is the fabric of space itself is growing. And as that happens, the photons that are trying to propagate through that space get stretched out. They lose energy. They become, instead of optical photons or ultraviolet photons, they become infrared photons. And the further away you look in the universe, the further back in time you look, because light takes so much time to get from there to here. The further away you look, the more that light is stretched out, the redder it becomes. And so an optical photon, or something that we could see with our eyeball, if it was released in the earliest parts of the universe, in the first tens of millions of years after the Big Bang, today, instead of being a 500 nanometer photon, that's just a reference, it would be 10 or 15 times longer in wavelength. And that's exactly the wavelengths at which the Webb Space Telescope is designed to operate. And so by moving into the infrared, because the light from these very distant galaxies that we really want to know about, because they tell us about galaxies as they were in the earliest times of the universe, that light from those galaxies is stretched out. And so this is why now you're sort of constantly seeing in the news, oh, astronomers discover the most distant ever galaxy. Oh, they do this again, and they do it again, and they do it again, okay? This happens about once a month now. And I swear that there are people who seems like their whole career is just to be able to have that press release that says, we discovered the most distant galaxy, you know, even though they're going to do it another 3 or 4 times at some point, okay? That's not the world I live in, or not the work that I do. So I can mock it a little bit, all right? All right, now I want to talk a little bit too about my involvement in the James Webb Space Telescope. Because ultimately what I'm going to end with at the end of this talk is, what are we doing? What are we trying to learn with the James Webb Space Telescope? But it actually is a really involved and long story, it turns out. Because when I was a graduate student in the 90s at the University of Wisconsin, there was a pamphlet that, or a big book, essentially, that hundreds of astronomers worked for many person hours on, that said, oh, what is the next generation space telescope going to be like? What is the successor to Hubble going to be like? And those were the initial seeds for what is the James Webb Space Telescope. And then there was a long and storied history of people coming into NASA administration and thinking that they knew how to do things better than other folks. And the mantra at that time in the late 90s was faster, cheaper, better. It's hard to do all those three things together, okay? And so Webb got started as something that was going to be a $500 million instrument, $500 million. It is not. It is more like a $10 billion instrument, okay? But it also has proven the worth of that investment. So my story actually starts in November 2020. And it's kind of odd because I am not an infrared astronomer. Typically, people come up with certain experiences and certain expertise. And my expertise was definitely not looking at light in the infrared. But I was really interested in the way in which gas and dust flow through galaxies. And I don't know what struck me and the, what crazy idea I had that said, you know what, I should write a proposal for the James Webb Space Telescope. Now, at this time, Webb didn't exist. It was still in the testing chambers at Goddard Space Flight Center. It hadn't even gone to Marshall, where they put it in the giant Apollo-sized, or the vacuum chamber they used to test the Apollo missions. So November 2020, and we all remember kind of what 2020 was like. This is my family. This is on the beaches, actually in the northern Indiana. So sorry, we didn't get up to Michigan, but at least it's Lake Michigan, right? And in November, I rented an Airbnb near Holland, Michigan, just over by the shore. And I spent about 5 days there, locked away with nothing but, Notre Dame wrote this story and I was a little embarrassed when they quoted me. They actually, like when they say they're going to quote you, you should be careful about what you say. Because I said, yeah, I locked myself away with, a bunch of food and a couple bottles of wine and I wrote this proposal, okay? which was true, right? So I spent those 5 days sort of at the kitchen counter of this Airbnb. And my first task was to say, okay, I want to look at this part of the sky. And I want to study this specific thing. Is it bright enough that it's possible that Webb could see it? Because that's the first thing you have to ask. If I'm going to suggest to NASA that we use this giant new telescope to do something, is it feasible? And that's actually really hard because the telescope didn't exist. There were some technical documents about how sensitive it could be. Okay, well, I can use those, even though they're kind of, they're approximations. And it was, I didn't know how to start from first principles, for example, and calculate how bright the stuff is that I was going to look at to see, okay, when I looked at Webb sensitivity, is this feasible? I kind of had to make it up. My best estimate is this, based on what we know here, there, and these other 4 bits of information. And so I literally spent the first 2 days just poring over technical documents, doing calculations, trying to figure out, could this be feasible? And on the night of the second day I was there, I thought, yeah, okay, it's feasible. Now, if you want to use the James Webb Space Telescope, you have to write a proposal. So I started writing. At this time, there were about, 4 pages of scientific documentation and justification, and a page of technical justification of why you could do it. I submitted it in late November 2020 at the end of those 5 days. And then I waited, okay? Again, November 2020, this was still at least a year away from launch. In March of 2021, I was actually really surprised. One of my collaborators said, have you checked your email? And I thought, well, why would I check my email, right? Because nothing good can happen there. Except that it was a message from the Space Telescope Science Institute in Baltimore, the organization that runs the scientific effort of both the Hubble and James Webb Space Telescopes. And it said, Dear Dr. Howk, we are pleased to inform you that the James Webb Space Telescope Cycle 1 proposal, that means the first opportunity to use the James Webb Space Telescope for your own science, is approved, okay, has been approved. By the way, when you get these emails, and for each proposal with the Hubble and with James Webb, we typically submit somewhere between 3 and 5 of these proposals from Notre Dame, something like that from our group at Notre Dame. You can tell right away in that very first line whether, yeah, you can stop reading. Actually, pleased to inform you means you can kind of stop reading because you can celebrate, right? Usually it says we regret to inform you, okay? But nonetheless, the way this happens is that you submit a proposal, transmit electronically to the Space Telescope Science Institute. They convene a panel of 100 and more astronomers. They break them up into sub-panels that have various expertise, And 8 or 9 experts in your field review the set of proposals that are trying to do things that are similar to yours. And they rank them. And they say then, well, which are the best? And of the ones that are the best, they get the time on the telescope. They get to tell NASA, okay, here's how we're going to point the telescope. Here's what we're going to look at. Here's how long to expose. Here's what instruments, what spectrographs, or what imagers to use, what filter colors to use, etc. And I was one of the lucky ones for this. Okay? Now, this seems great, March 2021. But remember, the telescope is still in testing, still on the ground. And in fact, it wasn't launched until 9 months later on Christmas Day, 2021. This was launched at about, I don't remember, it was between 5:30 and 6:30. I don't remember exactly the time, Eastern Standard Time. And so I drugged my mother out of bed to come watch the launch with me. I probably would not have done that if we didn't have time on this telescope coming up. I got really excited about it all of a sudden because of that, right? So it was launched from French Guiana by using one of the European Ariane 5 rockets. This is the last image of human cameras on the back of the James Webb Space Telescope. It launched from the Earth and then traveled about 1 million miles to what's called the Lagrange point out here, L2 point. This is a 1 million mile stretch, or it's 1 million miles away, on the far side of the Earth from the sun. And the reason for that is that as the Earth goes round and round the sun, and it pulls on this James Webb Space Telescope, and the sun pulls on the James Webb Space Telescope, the orbit of JWST matches that orbit of the Earth. It has exactly this 1-year orbital period, just the same as the Earth does. And because of that, it's also what's called an unstable equilibrium point, meaning that a stable equilibrium point is like trying to roll a marble down into a bowl. Once it gets to the bottom of the bowl, it just hangs out there. Nothing's going to change it, right? Unstable is if you flip the bowl over and you put the marble on the top. You can rest it right on the top if you work at it, but then if you give it a little nudge, it will not come back and stay there. It will go away from that. So Webb sits out here at a point where if it's perfectly aligned, it will be in an equilibrium point and it will stay there forever. But it's nothing's ever perfect. And so it has to use little bits of rocket boost every now and again to maintain its orbit so it doesn't fall off of that bowl and go away. Okay? This turns out to be the major limiter of the lifetime of the Webb Space Telescope. And in fact, the design, the sort of limit was to say, we want this telescope to last at least 5 years. And before I proposed and was successful for getting time, I thought to myself, $10 billion is a lot of money to spend on something that might last only 5 years, right? But it turns out the European Ariane 5 rocket booster was so precise that we know now that, if the rocket boost had not been that precise, Webb would have had to correct its approach to this. It would have had to use a lot of fuel to get right in that right resting spot. But the rocket itself was so good that instead of a 5-year lifetime, we now know it will be more than 20 years. Okay? So it was an amazing insertion of Webb into its orbit. Now, on its way out, Webb had to do a lot of work, actually. It unfolded its solar array. It unfolded its antenna for communication. It started to unfold that sun shield. And then eventually it unfolded the wings of the telescope, deployed the secondary mirror, and then was able to get to rest there. So there were something like, there were several hundred individual steps that had to be made in that unfolding of this telescope. And if one of them had failed, we would not have a working telescope right now. So this thing was engineered to within a hair of its life, I guess. I don't know how to say that exactly. So it was launched in December, unfolded itself on the way out to its resting spot. And then in February of 2022, it sent back this first image, which is really an out of focus image that is, the detectors were used to actually image the mirror itself. And so you can see the individual hexagonal segments here. You can see the deployed secondary with we can see the deployed secondary here, which is like an obstruction. This one is tilted a little differently than the other, and there might have been a star in there or something that was actually providing the light, and that's why it was lit up like this. The problem with these hexagonal telescopes is, if you look at your telescope here, or you look at one that you have in the backyard, it's usually either a spherical primary mirror or a parabolic primary mirror. And so Webb should have a parabolic shape in order to maximally focus light from the distant universe on the detectors. It did not there because each of the individual segments, they were actually purposefully misaligned from that parabolic thing because then they could lock them in place for the launch. And then it unlocked them and started to tip them back and forth so they could figure out where they were. And in fact, this is one of the early images that it took of a single star, but you can see it's not just one image of it there, right? That's because each of the mirrors is focusing its view of that star to a different place on the detector. And in fact, this should move. Those mirrors are out of focus and they're tilted in funny ways. And so what they did was they aligned them to bring the focus and everything else into a very sharp point. Okay, so it went from these aberrated images to a very, very sharp image. But now you've still got each of these mirrors focusing the starlight at a different place on the detector. So the next step was to point them all in the same place so that that light from each of these stars could be stacked on top of one another so precisely that we wouldn't know it's actually multiple mirrors, that it would just be a single mirror. And it looked like that. Okay. So they did an exquisite job of it. This is on March 16th, 2022, so about 3 months after launch. This is one of the first telescope alignment evaluation images. And the target is this bright star here right in the middle. And of course, when they released this, people who are kind of like me looked at this image and said, whoa, look at all the background galaxies that we already see. Because we didn't know, I mean, we thought this telescope was going to be spectacular, but we didn't really know, right? You never really know until you see it at work. All right, so what do you notice is funny about this star? It's got all these spikes, right? And you folks probably deal with that too if you have spiders in your telescopes. Those are what are referred to as diffraction spikes. But this one has 1, 2, 3, 4, 5, 6, 7, 8 of them. Why that? Because if you use your telescopes, you're probably looking at either 3 or 4. Okay? Well, here's why. So with a normal telescope that might look like this. This is maybe, if you look down the tube of a celestron or something like that, it might look a little like that, although they have spiders like this, if I remember correctly. What you see is the central obstruction from the secondary mirror, and then the support struts here and here. And then you see, of course, the primary mirror. So what happens is, as light goes by those support struts, and even the central secondary, it becomes diffracted. What that means is it's redirected a little bit. And that's what causes this diffraction, these spikes here, 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 and there. Those are from these support struts. But Webb doesn't look like that. It has 3 support struts, but it's got 6 of these, okay? And it turns out that's because there's a little bit of extra stuff that happens. All right, we got to dig a little bit into physics here, if everybody's okay with that, all right? And the idea is that if you take a circular aperture, you just look through a piece of paper or something like that. When light passes through a circular aperture or hits a circular mirror, what happens to even just a pinprick of light is if you stretch it enough, if you get into your image manipulation software and you look at the very faintest stuff, you wash out the central region, what you'll see is it looks a little like this. It's like dropping a pebble into a pond. It creates ripples. And those are the diffraction interference patterns of a circular aperture. Similarly, if you do a square one, you'll get something that looks like this. It's like a cross. In fact, you can see this. How many of you have screen doors in your house? Right? You ever looked at the sun or at a street light through the screen or through a screen on a window and you see the plus sign of the diffraction? That's exactly what's happening here. Okay? So if you have a square mirror, it will produce a diffraction pattern that looks like that. Webb has hexagonal mirrors. And because of that, each edge creates a diffraction pattern, and it looks like this. Okay? So that's one part of why we see those spikes with Webb's diffraction. It's not the only part. Okay? If you imagine, so this is looking at the struts of telescopes. If you have, again, the support struts that look like this, then what happens is the spikes that get created are perpendicular to those struts. And so it would look like this. If you have 2 struts crossed like you would in a typical ground-based telescope, then you get that plus sign. With Webb, it has 3. And so because of that, it produces these spikes. And in fact, what's really cool about the optical design of Webb is that they designed the support struts so that some of the diffraction from those support struts actually fits within the diffraction from the hexagonal mirrors. So if they had tilted them at all relative to one another, instead of 6, I mean, maybe you could have had 12 or something like that, right? But they kind of hid the diffraction spikes, these crossed ones here, from 2 of the supports within the diffraction spikes from the hexagonal mirrors, which is really clever, I think. All right, and then April 28th came along. This was about a month later, and they released this, which is a first image or set of images with all of Webb's instruments. Webb has 1, 2, 3, 4, 5 instruments on it. And these are images from each of those of nearby regions of the sky. And again, this, when you look at it, it starts to become really, really, really exciting if you're like me, because look at all the stars there and how well separated they are. That means the instrument is working really, really well. Now, that's April 28th. Meanwhile, I'm at home waiting for news on, well, when are they going to look at my target? Okay? And so I get an email on Sunday, April 24th, that says the program plan window notification. This is how they tell me, when are we going to observe your target? And so I think, well, maybe 6 months, maybe 8 months, something like that. This is in 2022, and they say January 2024. Okay? Yeah. Now, this is because with the Hubble Space Telescope and the James Webb Space Telescope, they're such expensive instruments that you want to be as efficient as possible. And so what they do is they try to, it's like a big puzzle. They try to fit things in as efficiently as they can in order to maximize the return from the telescope. Now, I've had this happen with Hubble many, many times. And typically what happens is, because I knew that the best window for observing this was in January of each year. That's when the sun is on the other side of the sky and the telescope is pointing in that direction, let's say. So I figured what would happen is, well, they'll email me in another couple months, and they'll tell me that the plan has moved up to January 2023. That's only 9 months from this email. And I actually did get, like 6 months later, I got another email that said, hey, plan window changed. And I got really excited. And instead of January 5th through January 23rd, 2024, they moved it to January 5th to January 18th, 2024. So they didn't actually move it. They just constrained it a little more. And yeah, that was really depressing. In the meantime, in mid-July or in mid-2022, they started releasing some of these images that you've seen before from Webb, the first light images. This is the so-called Carina Nebula, a star-forming region in our own Milky Way. You can see these, what we refer to as the cliffs here of star formation, these dense molecular clouds with stars forming within them. One of the features of Webb is, well, all right, firstly, infrared light. You cannot see it with your eye. And so when you see this very, very colorful image, take that with a big grain of salt. Because what's happening is there's an artist's impression that's trying to maximize kind of the scientific interpretability of the image. These colors are not connected to the wavelengths of light, except that they tend to put the bluest colors, that is the shortest wavelengths, in blue, and the longest wavelengths in red. Okay, so they order them appropriately, but the colors are not actually colors. And what you see here is that this is actually a composite of 1, 2, 3, 4, 5, 6 images taken in 6 different filters to isolate different wavelengths, different colors of light. At the same time, too, Webb has multiple images, or multiple instruments, including multiple imagers. And this is an image of both this, what's called NIRCam, the near-infrared camera, and the mid-infrared instrument, MIRI, which is the one I'll talk about a lot later. And you can see kind of the different view that you get as you go to different wavelengths. MIRI has longer wavelength, or detects longer wavelength light than NIRCam does. This is just to show, again, that typically the near-infrared camera is on the short wavelength end of the infrared, the mid-infrared camera is on the long wavelength end. And so here's a region of the sky with the near-infrared camera, the short wavelength camera. Here's what a nearby region of the sky looks like with the long wavelength camera. Okay, they give you much different views. Yeah. That's just to show you colors and how they put them in there. Again, from the first light images. This is an image of a star, much like the sun, that has died. It's kind of gone gracefully into its death, and it's just released its outer layers. The solar system would fit kind of down in there, okay? So just know we're all going to die a fiery death in 5 billion years or so, okay? And we'll start to look like this. Just to give you a sense of what this looks like compared to the previous best imaging of this, this is from NASA's Spitzer Space Telescope, which was launched in the early 2000s, and this is what it looks like with Webb. So you can immediately see the difference. It's a much bigger telescope, so it's much more sensitive. This is an image of a region that's referred to as the Tarantula Nebula. This is the brightest star-forming complex in the Large Magellanic Cloud in the southern hemisphere. And what's really cool about this is, again, just to look at the sharpness of the image here and how much detail there really is. This lies about 150, 175,000 light years from the Earth. Okay, so that's quite far away. And we're seeing this giant collection of some of the most massive stars that we know in the universe, all sitting down there together. One of my professors at Wisconsin one time wrote a paper that said, because in the old days you could not separate those stars one from the other, and so he said, well, you know, there's so much light there that maybe it's a single star that's 1,000 times more massive than the sun. And when I asked him about it, he said, you know, I actually didn't believe that, but I thought if it turns out to be that, I wanted to be the one who said it first, okay? And it turned out, you know, in their paper, they're very clear. They say it's either 1,000 solar mass star, or it's like 40 stars, each of which is 100 to 120 times the mass of the sun. And, you know, we find it really hard to imagine there are 40 such stars in one really, really tiny place. Well, the Hubble Space Telescope came along and imaged that and said, oh yeah, there actually are 40 of those really supermassive stars, and they're all packed together, just like you said. In your alternative explanation. This came out about 3 months ago, and it's one of my favorite images from the James Webb Space Telescope. When I look at this, my initial impression is it's somebody at an art fair who's done a lot of like, you know, maybe on a black velvet towel or something like that. They've kind of spray painted it and made it look like this. Because you can see, you know, normally when we see images from these telescopes, you see a star forming region, or you see distant galaxies, or you see the gas. They're never kind of mixed all together like this. And yet this is a real image of the sky. This is in the so-called Small Magellanic Cloud, again, about 200,000 light years from the sun. And it's another star-forming complex that is energizing the interstellar gas around it. If you looked at this with Hubble, you would see none of this stuff over here in these dark patches, because there's so much dust in the way that it absorbs all the light from those background galaxies. But with Webb, you can see it just peers right through and finds all these distant galaxies that are thousands of times more distant than the stuff in the foreground here. It's really amazing to me. This is one of my favorite images that Webb has ever taken. Webb takes a lot of images of what we refer to as gravitational lenses. This is large clusters of galaxies that are so massive that when light goes by them, they redirect the light, they bend it, and they warp our images. So this stretched out orangey thing here and even here are actually the same galaxy, just off in the distance. And because of the way that the light, as it comes to us, interacts with these foreground galaxies, it gets misshapen, right? It gets magnified and blown up, right? So there you can see what the thing looks like in detail. You can also see, look at this thing, right? You notice that it's like a pair of things that look about the same. That's the influence of gravitational lensing. If you want to see something even more spectacular, well, I'll come to what I think is the most spectacular one. Here's another example, a giant cluster. And these arcs that you see here are background galaxies whose light has just been stretched out by the massive gravity of this foreground system. And if you look at this, what's most spectacular about this to me is, this is again from the first images we got off of Webb. On the left column here is what it looks like in the Webb data. On the right column is what it looks like in Hubble data. Hubble's a great telescope, but it can't see things this far away nearly as sensitively as Webb can. There should be another column. Here's another example. Here are galaxies, these orangey ones here, that almost completely disappear when you look at them in Hubble. They're only seen in Webb, which means they have to be in the very distant universe. I love this image. Yeah, please. Yeah. Yeah, so the reason Webb can be so clear like this is that it's above the atmosphere. That's the first thing. It's such a big telescope. That's the second thing. And again, putting it far away from the Earth means that light and heat from the Earth can't influence this telescope very much. And so it can't make it glow. So in a sense, the clarity, like the precision, that's not exactly influenced by the fact that it's so far away. But the fact that we can see this at all, as opposed to just a white screen of bright light from the telescope, is affected by that. Okay. And please, by the way, interrupt. Feel free to ask questions. I've been talking a long time. I apologize for that. Okay. Yep. Yep. This is another case, a single galaxy warping the light from a single background galaxy here, and it gets stretched out like that. And the moment, well, pretty much every astronomer, when we saw that, immediately thought of this Dolly painting of the clocks, right? That it looks just like that. And then what I think is the most spectacular of these lenses is this. again, that to me looks like something that somebody painted as an artist's rendition of something, and I would have said that's completely fake, okay? But it's not. This is actually data combined from the Hubble Space Telescope and the Webb telescope. And what you see right there in the middle is a single massive galaxy. And there is a single background galaxy that is so well aligned with that foreground massive system that the light and the gravity from this foreground central bit here is warping the light from that background galaxy as it comes toward us. And it stretches it out into this misshapen thing. Okay, we use these a lot because what's interesting about this is it magnifies, it's like a magnifying glass. It stretches out the light, which means we can see things more, we can see smaller scales on those background galaxies than we could otherwise. And it turns out to make them brighter. Okay, so this is really spectacular for an astronomer. Oh, the other thing that it does is it turns out sometimes this gravitational lensing is so powerful that we can see individual stars as they pass by a place where the magnification is really, really high. Those stars will show up like individual stars like the sun that are 10 billion light years away. We would never see them if it weren't for this combination of Webb and this gravitational lensing. And we can see supernovae that explode in these galaxies. And then we see them sometimes multiple times. If a supernova explodes there, that position in that galaxy is also perhaps over here and over there because of the way that the bending of that light works. And so we actually see them typically 4 times. And we wait because there are delays. The light to go one place and the other follows different paths through the universe. And so there's a delay. We see the supernova explode, and then a few weeks later it explodes over here, and a few weeks later it explodes over there, and a few weeks later it explodes over there. It's really crazy and spectacular. This is a galaxy like the Milky Way, observed with Webb's MIRI instrument, the mid-infrared instrument that looks at longer wavelengths of light. This is M74, which is also NGC 628, if you're used to that one. And what you can see, MIRI isolates the gas from this dense molecular material. When you see dust lanes in a galaxy by looking at its image, now they're glowing in Webb. This is just an example. This shows the same galaxy. On the left is a Hubble image, and on the right is a Webb image. Oh, I'm sorry, in the middle is a Webb image, and on the right is the combination. No, I mixed that up again. Hubble, Webb, combination in the middle. And what you notice is these dust lanes that you see here. Those are usually tracing in spiral arms the dense molecular gas where new stars will be formed. And here, this dense dark lane becomes some glowing vortex of material over there. All right? So this really excited me. This was really spectacular. Here's another example. NGC 7469, it's a barred galaxy. See these big dust lanes here. There's another one over there. There's another one over there. And when you look at it in Webb, it has this ethereal glow. Okay? So Webb gives us a completely different view of galaxies in the universe. It also, of course, this is a family portrait of planets in the solar system. Jupiter, of course, you notice there's the big red spot. In fact, it's glowing. It's brighter than a lot of its surroundings. There's Saturn, which you would recognize. It's dark because methane in the atmosphere, and when it was taken in a filter that isolates methane absorbs a lot of the light, so it doesn't reflect as much back. The rings, though, don't have methane, so they're bright. Here is Uranus with its rings, and Neptune with its rings as well. Did you know Neptune had rings? I knew Uranus had rings. Neptune was a little odder to me. I'm not sure I knew that before I saw this. Here again is a star like the sun in its death throes. Oh, I take that back. I think this one is a young star forming down there in the first time, sorry. And it's blowing a wind that is shaping these cavities out here. Each of these colors is a different filter, and those filters isolate specific physical processes. If I remember correctly, the orange here is molecular hydrogen that's being excited by this, okay? And then this is one of my favorites. It looks a little blurry, the diffraction spikes are in there and everything, but this is a binary, what's called a Wolf-Rayet star. It's a binary star, and the star itself releases these periodic pulses that eject dust. Well, if I throw something up in space, you know, I'm on the moon or something, and I throw something up, and it starts drifting away, and then I throw another thing up, and it starts drifting away, and I throw another thing up, and it starts drifting away. Well, they're in a line, okay? Well, here, it's releasing dust almost in a circular pattern, and that dust releases and drifts out, and then the next pulse happens, and it drifts out in the next one, okay? And so you can see these shells that are centered on the central star of this dust and gas that's released. In fact, the next image I'm going to show you, which is another view of this, was done by a former grad student mate of mine, Jennifer Hoffman at the University of Denver. And what it shows is she and her graduate students went back and took another image of this. This was in July of 2022. And her group took another image about a year later. And what you see here on the right is if you take a slice along this and look at this little triangle, this triangle here is on the bottom, this triangle there is on the top. And what do you notice? Those rings have moved. Just in a year's time, we can watch the motion of the rings. And so we can figure out how quickly they're moving. And then, of course, it does boring things. It looks for planets around other stars. This is, a very romantic name, HR 87999, or 99, right? HR, that's the Bright Star catalog, isn't it? I don't remember. Any rate, and what you see here is the star has been blocked out. Webb has the ability to put a little disk in front of the star so that it hides it, the star's light, because otherwise, again, it would be like standing underneath the streetlight. And you can see these 4 planets that show up in this case. So this is a direct image of planets around another star. Be a little wary when you see things like this, because if you tried to look for the Earth around another star, you would never see it. These have to be planets that are super, super, super young. They're still having material fall down from their natal disks onto the planet. So they're really hot and they're really puffed up, which makes them large. And anything to make something bright, you either make it really hot or you make it bigger. And so these planets are bigger than normal. All right. A lot of words. I hope the images have been helpful to sort of make that more interesting than just my words, okay? But I do want to talk a little bit just at the end here about galaxies on the edge and what we're doing. This is the Cigar Galaxy, M82. It's a galaxy about 6 million light years away from Earth. And what's really spectacular about it is that, so this is M81's companion, one of its companions, that there's a huge burst of star formation happening right down in the core of this galaxy. And what that means is, when you form a bunch of stars, a bunch of them die pretty quickly. And especially the most massive stars, they all die right away in the first 10 million years or so after star formation, maybe 100 million for the tail of it. So if you form a lot of stars, they die altogether right away. When they die, those massive stars don't go peacefully like the sun will. They explode as supernova explosions. And when they do that, they superheat the gas around them. So it's kind of like setting off a bomb in the atmosphere. In fact, kind of macabre story, but long ago when they were building atomic bombs, they realized that, well, we only need to make them so big, because if we make them any bigger than that, they just pop the top off the atmosphere and all the energy goes up, okay? And what happens in these galaxies is, right down in the core, there's so many stars being formed and they're all exploding at the same time that they pop the top off this galaxy. They explode, they superheat and create a bunch of hot gas, and that expands vertically. And as it does, you can see it as what we call a wind. It's escaping right here. That's what it looks like in the optical. When the Spitzer Space Telescope looked at it, it looks like this on the same scale. And what you notice is this red stuff. The red stuff is through a filter that isolates light at 8 microns, so 8 micron light. And it turns out that is light from, I'm going to use a very technical phrase here, that is light from polycyclic aromatic hydrocarbons. If you've ever stood behind a poorly tuned car in the old days, or even a diesel car, something like that, you've taken a deep breath and you're like, oh my gosh, all that, the fumes and everything from it. Half of that is poorly combusted gasoline, which is in the form of polycyclic aromatic hydrocarbons, all right? So it's just organic molecules, it turns out. Or when a chemist says organic molecules, they just mean carbon molecules. And they are shaped a little bit like this. And stars in galaxies make these because they burn things incompletely. The stars like the sun, when they get old, will do this. And so we can use it as a tracer of where matter is getting pushed around. And in fact, I did my thesis inspired by this galaxy. Okay? This is NGC 891. It's in the Andromeda constellation. It's a disk galaxy like the Milky Way. And this is why we talk about the title here is Galaxies on the Edge. It's seen edge on. And what I studied was, if you notice, all right, there's the central dust lane, kind of like when we look at the Milky Way, but look at all this stuff out of the plane. All of this dusty material, all these opaque clouds that are sitting up there. Those had to get up there somehow. And so this, as opposed to a galaxy like the Cigar Galaxy it has a central starburst that blew up a lot of stars all at once, this is kind of a more normal galaxy like the Milky Way that's sort of percolating a little bit. And so my thesis was on looking at these regions of dust above the galaxy and trying to explain how they get there. And then I left that aside for 20 years or so, something like that, until the James Webb Space Telescope came along. And I said, well, what's the first thing I want to look at? I want to look at this. Okay. This, by the way, again, this is what we looked at when we saw a face-on galaxy. I wanted to do it for an edge-on galaxy. So if we zoom in on the central region of that, this is, again, that same galaxy, seen where it's just put the plane across. And I'm going to fade into what we got with the James Webb Space Telescope. And you can see that it looks a lot different. Firstly, the central disk is all lit up, okay, because that's stars being formed and we're tracing the energy from those stars. But then all of those filaments, instead of being dark splotches, are now glowing. Okay? And in fact, this is about 2,000 light years stretch. So this material that you see up here, which we see out to about 25,000 light years above the plane of this galaxy, has all been ejected by starlight, or by stars exploding. If you want to zoom in and look, you can see a bunch of stars in here, of course, but then this sort of forest of filaments, some of which are extremely large, thousands of light years long here. There's another one that just pops out of the top here, okay? And so this is what we're trying to study, is this almost hair that's growing out of this galaxy. And in fact, this is just to sort of fade back and forth a little bit between the optical image. Let's see if I can repeat that. I don't know if I can, actually. There we go. Between the optical image and the James Webb Space Telescope image. Okay. Just to show you, yes, what we saw before in absorption, we now see in emission. All right, so an advantage of that, and I'm going to show it in a different display here. This is a grayscale view of it because it provides a little more contrast, even though the colors aren't as pretty. And again, you can see everywhere above this galaxy are these just filaments and clouds and all sorts of clumps. To be honest, we got this in January 2024, and we still kind of haven't scratched the surface about what it all means at some level. Part of that's because the data processing has been really annoying. But let me show you another view of this, which is to highlight, this highlights the brightest parts of it. But now I'm going to saturate those and show you the faintest parts. Whoop, that is not what I meant to do. Less impressive when I screw it up, right? And again, this is just the same image looked at in a slightly different way, where you can see the stuff way out above the galaxy. There is material up there everywhere. Now, what we're trying to do at some level is try to firstly find a way to quantify all of this, make mathematical identifications of it and everything. So if we take this little section here, we're working with Susan Clark, who's now at Princeton. There's that filament that you see in the data, and she has a way of identifying where so-called filaments are in these images. And they look a little bit like this. And what's really cool is that we've been able to show, and this is sort of for the first time, we expected that those filaments get there because when you form a bunch of stars and they explode, it ejects material. We're able to show that above the heavily star-forming regions in the disk, the filaments are pointed upward. They're vertical. They're perpendicular to the plane. And when you go elsewhere above the kind of lightly star-forming stuff, they're kind of everywhere. They're just random. All right, so this is the first direct evidence that we can show, look, above these star-forming regions, this stuff is flowing out. And so the general idea is we're trying to take images like this, where we look at a face-on galaxy, and we look at an edge-on galaxy. And we're trying to trace the history of star formation. So in a spiral arm, the gas flows in, creates dense clouds. They form stars that are here in the pink. And when they blow up, they make these super bubbles. And that's kind of what you could see, giant bubbles here in this face-on view. And we're trying to look at it from the side, where we can see what happens, what's the vertical structure of those bubbles like. And when we put the two together, the idea is we get a complete picture of what is the life cycle of gas and the metals, the oxygen and carbon, nitrogen, things like that, that are life-giving, if you will. How do they get formed, get ejected out of a galaxy, and then reincorporated into it for the next generation of stars and planets and, maybe little green men or something, okay? All right, that's all I have. I wanted to kind of, you folks really are the first to see this kind of outside the hallways of Notre Dame. And I hope that you get it. I hope you can hear that I'm a little excited about it, all right? So I get worked up. I hope you folks are a little excited about it as well. And I am more than happy to answer any questions you may have.